Okay, so welcome to Lab 5 of Physics 2212. My name is Cooper Allen. I'm in Section X21. This lab is meant to observe the effect of a non-ferrous conductive metal tube on a bar magnet in free fall through it. Of relevance to that are Faraday's law, the Lenz law, the magnetic force of a current-carrying loop, and the magnetic field, and therefore force of a dipole, which represents the bar magnet. Some assumptions we had, first, modeling. We're using closed-script simulations to model this. The system here is the bar magnet, the foil tube, and Earth, just because of gravity. Everything else is surroundings. Assumptions, negligible air resistance. There really isn't much to assume here. Take G equal 9.81, everything like that. Preview of results. Using the data from Lab 3 for my magnitude of mu, which is probably skewed a little bit lower than it should be, the simulation shows it should take about 0.34 seconds to fall through. In reality, it took 0.8 seconds, which actually corresponds to a mu mag of about like 1.5. Here pictured is the graph from the Lab 3 data. Here's all my code, all of the parts that we had to input our own things. You can see there's the mu magnitude from Lab 3. These are all the dimensions I had for the actual tube, and I have pictures of that. They're not actually in the PowerPoint, but some functions for the magnetic field of a bar magnet, etc., etc. We've got a whole bunch of stuff in here just to make the code work. It goes through kind of integrating, the velocity is, this is inside of a loop, which is why it's, adding on to itself at the end, all that kind of stuff. Gravity. Yeah. So we had some questions in the middle of it. The first question was about when we simulate it, it goes like red and blue. You can see the blue at the bottom here, and figuring out which one is clockwise, which one's counterclockwise for the current as it goes through. The red bit is the counterclockwise bit, the blue bit is clockwise. There's another question about the dynamics of the system. Nothing actually changes when you flip the direction of the magnet. So if you drop it in North Pole first, it has the same effect as dropping it in South Pole first. Yeah. And then the other question is, in real life, it took about like 0.8 seconds to fall through the tube, which is about double what the simulation predicts. It's likely due to faulty info from Lab 3. And then the last question I answered just by using the mu mag that I thought was more true to life, that gave me the right fall-through time, which creates this graph, which is very telling of here's the time that it is falling into the tube. In this time, it is fully surrounded by the tube, and so it has a magnetic field pulling up, or pushing up, and pulling up. So pushing up from the bottom and pulling up from the top, whereas at the top it only pushes up, and at the bottom it only pulls up, and so it cannot as effectively counteract gravity, which is why you see these little tails on the end of an otherwise flat velocity graph, indicating that the force from gravity is about the same as the force from the tube, canceling out to zero acceleration and thus no change in velocity. And the last, the what-if questions. Basically, the lower the resistivity, the less of an effect it has. If the resistivity were basically zero, the magnet would experience almost no deceleration as it passed through the tube. And then also, cutting holes or slots into the tube would destroy some, if not all, of the infinitesimally small rings that make up the tube, which would render all affected rings essentially useless in decelerating the magnet, as any incomplete ring would not create a full circuit and thus couldn't carry current, and thus could not provide a force to resist it. But yeah, that is my Lab 5. Links to this code will be in the description. Hope you enjoyed, and I will, see y'all later. Bye.